Well, hello there. I don't know about you, but I find number 36 from chapter 20 a little conceptually challenging. It's not about the calculation. The difficulty is that you need some familiarity with important ideas from the theory of probability. So I think we should review some of those concepts from probability, some of the basic ideas, and we'll use the classic coin toss to do that. So for the next few minutes, I'm going to be talking about an example that's not directly related. Well, it is directly related, but it's not the actual scenario in the problem. Suppose you are interested in tossing a coin 4 times in a row and observing the number of times that you get heads and tails or various combinations. So your first toss, of course, can come up two ways. You can either come up with a head. Whoops. Let me grab the pen here. You can either get a head or a tail. And I'll put the number 1 over here to indicate this is the very first toss. And I think I need a slightly thinner pen line here. You know what? I really should put these farther apart because I'm going to have some branches coming off here. I need some room to spread out. So I'll put heads here and tails over here. This is your first toss. Those are the two possible outcomes. And even though one side of an actual coin, like a US quarter, is probably a little heavier than the other, I'm not sure. Let's imagine this is an ideal coin where these two outcomes, heads versus tails, are equally likely. So that means you're 50% likely to get a head or 50% likely to get a tail. And what that means is if you were to toss the coin 1,000 times, then something like 500 of those times you'll get heads. That's the meaning of saying you're 50% likely. It doesn't mean that you actually will toss exactly 50% heads. We all know that. If you were to toss 1,000,000, you could expect something close to 500,000 heads and 500,000 tails. Okay. Now this for the second toss, suppose you had come up with heads the first time. I've lost my cursor. Here it is. So suppose you would come up with heads the first time, and then you go to toss the coin a second time. There are two possible outcomes. You could then get a second head or heads, or you could get tails on the second toss. Or supposing you had tossed tails the first time, you could then toss heads or tails. So this row here are the possible outcomes of the second toss. And so this is starting to look like what you might call a tree diagram. I think sometimes people call that. We've got branches on the tree. I count actually 1, 2, 3, 4 total branches. And those 4 branches show you the outcome, the possible outcomes for the whole thing, not just the first toss or the second toss, but you could ask, what are the possible outcomes for 2 tosses in a row? Well, there are 4 possible outcomes. You could have tossed a head and then a head, or a head and then a tail, or a tail and then a head, and then a tail and a tail. And I think off to the left, I'm going to count the outcomes for each toss. So there are 2 possible outcomes for the first toss. So that would be 2 to the first. And then there are 4 possible. No, I shouldn't talk about outcomes so much. This second row here has 4 objects in it, which is 2 squared. Okay, now, what if you then toss the coin a third time? Well, if you had tossed heads first and then heads again, then you could toss heads for your third toss or tails. All right, you get the idea. I'm just going to fill out the tree here painstakingly. Okay. So this is the third toss, and the number of items in this row is 8, which happens to be 2 to the third. And I don't think I'm going to make a last row here. I think I'll move on. But let me get a different color. Ooh, I'll use the highlighter for the first time. Let me be fancy here. Okay, I'm trying to select yellow. Is it working? Yes. Let's focus on one specific outcome. It's possible that in this procedure of tossing a coin 3 times in a row, it's possible that you first tossed heads and then tails and then heads. That is one possible outcome of these several possible outcomes of tossing a coin 3 times in a row. Now, how many total outcomes are there possible? You could count all the branches. So can you see my cursor here? We've got this leftmost branch, 1, 2, 3. That's the one I highlighted, and then 4. It's pretty clear there are 8 possible overall outcomes for tossing a coin 3 times in a row, and I've highlighted just one of them. So it should be fairly intuitive now, the answer to this question. In a coin toss where you toss it 3 times, what is the probability of tossing heads first, then tails, and then heads? Notice I'm not saying what's the probability of tossing 2 heads and a tail, because there are actually multiple ways of doing that. For instance, let me get a different highlighter color. If I highlight this one, this is also an outcome that involves 2 heads and a tail. I'm being more specific than that and asking, what is the probability in 3 coin tosses of tossing a head, then a tail, and then a head? Well, only one of these branches is that desired outcome. And here's a very critical point. If this coin is true, I suppose you could say, perfectly balanced, and you didn't do anything biased with these tosses, then all of these outcomes are equally likely. You're just as likely to toss heads, tails, heads as you are over here to toss tails, tails, tails. All of those are equally likely. They're all equal branches on this tree of outcomes. So you could, hopefully it's intuitive that the total, or I should say the probability of this yellow desired outcome, I'm going to call it the desired outcome for now. And I'll abbreviate that probability capital P. Whoops. Go back to the pen. That probability would be, let me do this, the number of desired outcomes divided by or compared to the total number of outcomes. Okay, now, in this case, because of the way I'm posing the question, the desired outcome is heads, tails, heads. And there's only one such desired outcome. So you take that number 1 and you divide it by the total number of outcomes. Now, can you see the total number of branches here? You could count the branches and you'd get 8, or you could also just look at the terminal points of the branches. There are 8 of those as well. That's that 2 to the third. Okay, so since each of these possible outcomes for 3 tosses is equally likely, then the probability of obtaining just that one desired outcome, heads, tails, heads, what did I say? Heads, tails, heads, is merely 1 out of 8. The probability is 1/8. What is that, 12.5% probability? That's a really important idea that we need to do this problem. Now, if on the other hand, I'll just put or. Here's a different example. What is the probability of tossing 2 heads and 1 tail where the order doesn't matter? That's a little more difficult. We have to go through and count. This is not one of them. Green is one of them. Yellow is one of them. This branch is not. So we've got 2 so far. Here's another one. So that's 3 possibilities so far. This one doesn't count. This one doesn't count. And this one doesn't count. So it looks like there are 3 ways. Let me grab the highlighter one more time. Come on, having technical difficulties here. And highlight the last example I saw of 2 heads and 1 tail. So it looks like there are overall 3, did it again. 3 desired outcomes, if your desired outcome is 2 heads and a tail, out of the total 8. So let's see, 12.5% times 3, that's 25. So what is that, 37.5%, I think? Whatever. Your probability is 3/8 of tossing 2 heads and a tail in any order. But the important point is that all of these, in order to use this formula, all of those outcomes have to be equally likely. Okay, now there's another way. By the way, let's rewrite this here. This is 1 over 2 to the third, of course. And you could even write that as 1/2 to the third. You know, normally my handwriting slants the other way, and now it's slanting to the left. That must be because I've got the tablet sitting weird. I'm still new to this. Thanks for your patience. Okay, let me just get rid of some of this garbage here. I will pause and clean up the board. Okay. So I could write that as 1 over 2 to the third, which is the same as 1/2 cubed. And that might be a better way to think of it. Here's why. Okay, once again, we're asking what is the probability of tossing heads, tails, and then heads in that order for 3 coin tosses. That's the yellow path that I'm looking at here. Well, here's how you can think about it. You have to consider the likelihood of each stage. So when you start out with your first toss, in order to get that yellow path, your first toss needs to be a head. Well, what are your odds of getting ahead that first time? 50% or 1/2. So after you've already tossed that head, what are your odds then of getting the correct second toss? Tails. Well, 50% of the time you do the first toss as desired, heads, and then among those times, 50% of the time, you'll then get the correct second toss. And then among those times, 50% of the time, you'll get the correct third toss, which would be heads in this instance. So if you think about the overall process of tossing the coin 3 times, you're going to get that desired outcome of heads, tails, heads, 50% of 50% of 50% of the time. In other words, 1/2 of 1/2 of 1/2 of the times. In other words, 1/2 cubed. And that's probably a more useful way to think about it because it carries over well to a lot of other problems in elementary probability. Okay. Now, if you wanted to then apply that way of thinking to the question, what is the probability of getting 2 heads and a tail in any order, then you would use this formula, the 1/2 cubed for each specific outcome, and then just add up the number of times, or add up the number of different specific outcomes that are equivalent to that desired outcome. So in this case, there are 3 of them. You would add up 1 plus 1 plus 1 for the various highlighted paths there. Okay. Many of you probably are familiar with these ideas. Hopefully that was a good review for those of you who are not. Or I guess it wouldn't be a review. First exposure. I'm telling you, probability can really hurt your brain, even though you're not doing a lot of integral calculus when you take an elementary probability class, but you really have to think hard. Okay, so now we can move on to the problem at hand. And this is all messed up, so let me fix this. All right, here is the premise of the problem. They tell us that you have 2 boxes into which several balls have been placed. Now, I chose a specific number 6 here, 4 on the right, 2 on the left. Why am I telling you that? That's obvious. And you're told that once a second, one of these balls is chosen at random and switched to the other box. And then you wait a long time. You keep doing that every second for a long time. And then you start recording each second let's say at the same time that you move a ball randomly from one box to the other, you record how many there are in each box. And you do that 10,000 times. And there's already a problem with that. Some of you may have been scratching your head as you thought deeply about this problem, and I was doing the same. I think this problem could have been posed a little bit better. And the issue really is with this business about switching a ball from one container to the other every second. It's a problem that frequency is the same as the frequency with which you observe the boxes to see how many are in each. So let's instead think of it this way. Let's say many times per second, maybe even a billion times per second, these balls are zipping back and forth randomly between the boxes, maybe because we're actually talking about gas particles, which we know move very quickly, and there's a tremendous number of them in a macroscopic quantity of gas. So I've drawn a barrier here, but let's just pretend there's some way for each of these gas particles to move from one side to the other. Who cares about the details? The line is just there so that we remember there are two containers, two boxes. Okay, so they're zipping back and forth constantly. But once a second, which is way less frequent, once a second, you're going to actually take a snapshot of the configuration and count how many balls are in each side. And this is actually a lot like the coin toss, because each particle or ball is like a single coin toss. When you toss a coin once, you can come up with heads, you can come up with tails, they're equally likely. And the same thing is true for each of these particles. Because they're all zipping back and forth rapidly, then when you freeze time and go to check where one particular ball is, it's a toss-up, no pun intended. You've got a 50% chance of finding it on the left box or in the left box, and a 50% chance of finding that particle in the right box. So if you want to make a connection, you could even write heads, where's my stupid pen? Heads above one box, tails above the other. So checking to see which side of, or which box a particular ball is in is exactly like tossing a coin once. You could either find the ball in the left box, which is like coming up with heads, or you could find the ball in the right box, which is like coming up with tails. Now, previously, I used the example of tossing a coin 3 times in a row and looking at the overall outcome. What we're doing now is asking, hang on a second, let me reflect on this before I misspeak. Now added identifying labels to the balls so we can connect this more easily to the previous example. In the previous example, I asked, what's the probability of the specific outcome, heads, tails, heads? That's heads on the first toss, tails on the second, and heads on the third. Well, to connect that to this example, I could ask a question like this. You know, we've let these particles zip back and forth randomly, and we freeze time at a particular instant. And I ask the question, what is the probability of finding ball 1 on the left side, ball 2 on the left side, and then balls 3, 4, 5, and 6 on the right side? That's a very specific configuration of the balls. That's our desired outcome. And there's really only one such desired outcome. And we would have to divide that by the total number of possible configurations. So for instance, an alternate configuration would be balls 1, 2, 3 on the left side and balls 4, 5, 6 on the right side. That's another specific outcome. So how do we go about counting all of those? Well, that's one way to think about it. But, I'm going to use the second way of thinking about it that I just presented with the coin toss example. Let's go in order, balls 1 through 6. So the probability of having the overall outcome illustrated here can be thought of like this. Well, first, ball 1 needs to be on the left side, and there's a 50% chance that that's going to happen, or a 1 in 2 chance that that's going to happen. Now, assuming that's true, you then have a 50% chance of ball 2 also being on the left side. Assuming that is true, you then have a 50% chance of the third ball being on the right side. Assuming that the prior 3 assumptions are true, you have a 50% chance of ball 4 being on the right side, etc. So all told, you can kind of work backwards and say 50. You will find ball 6 on the right side, given that ball 5 is on the right side, given that ball 4 is on the right side, etc. 50% of 50% of 50% of 50% of 50% of 50% of the time. Does that make sense? So the probability of this particular configuration being the outcome is 1/2 raised to the 6th power. So you only have a 1 in, what is it, 64? 2 to the 6 should be 64. 1 in 64 chance of finding this particular outcome. Now, fortunately, we don't have to count up all the different outcomes for this example, because we're looking at a simpler type of outcome, which I'll get to in just a second. But I want to once more emphasize the connection between this example and the previous example. Asking which box a particular ball is in is like asking the outcome of one coin toss, but asking the probability of this configuration, considering all 6 balls, is equivalent to asking for the probability of a specific outcome for all 3 coin tosses together. Okay, now, in this problem, what they tell us is of the 10,000 times that you check once a second to see how many balls are in each side, there are 80 times when you find all of the balls in one container or the other. So let me clean up the page here. Give me just a moment. Okay, I'm going to attempt to explain this clearly. I mean, that's always what I'm trying to do, right? I hope. Suppose you did this 1 billion times. This business of freezing time and checking to see which boxes all the balls are in. And I'm interested in calculating the probability of seeing the specific outcome where all 6 balls are in the left box. Okay, well, if you actually did this 1 billion times, freeze time while these balls are bouncing around between the 2 boxes and check to see which box they're all in, 50% of the time, so if you did this 1 billion times, something like 500 million of those times, you would find ball 1 on the left side. So let's concentrate now on those 500 million times where you actually did find, and I say 500 million, but it could be approximately 500 million. Of those 500 million times where you actually did find ball 1 on the left side, half of those times you would also find ball 2 on the left side. So of those 500 million times that ball 1 was on the left side, 250 million times you would see ball 2 also on the left side. Of those 250 million times approximately that you found both balls 1 and 2 on the left side, half of those times you would likely find, or you would find ball 3 on the left side. So it's the same reasoning. Half of the time of half of the time of half of the time, etc. It's like I'm working backwards. So the probability of finding all 6 balls on the left side when we freeze time, I'll call that probability P. Oh, let me try that again. What's happening? Okay. That probability would be 1/2 to the 6th power. Because you're 50% likely to find ball 1 on the left side. And if that were to happen, then you're only 50% likely of also finding ball 2. So it's multiplicative. And I don't know about you, but the first time I was introduced to these ideas, they kind of seemed maybe obvious or intuitive. And then I thought about it more and it didn't seem so intuitive. And I think it's because I hadn't really thought about it very deeply. So you really have to be careful when you're counting numbers of outcomes. I'm telling you, elementary probability theory, not trivial. Okay, so 1 out of 64, that is the likelihood of finding this specific outcome, all 6 balls in the left box. Now, what if the question we asked was slightly different? What is the probability of finding all the balls in one box or the other? Like they're all in the left box or they're all in the right box. We've already calculated the probability of finding them all in the left box. Hopefully you can see that the probability of finding them all in the right box would be exactly the same. So we would just add those two to find the total probability of finding them all in the left box or all in the right box. This one accounts for all of them in the left box. This one accounts for all of them in the right box. And so we could write that as 2 times. There are 2 ways of getting this desirable outcome. And what I'll do now is replace that 2 with an, I'm sorry, not the 2. Let me replace the 6 with an n, where n is now the number of balls, or number of gas particles, if you'd like to think of it that way. After all, that's the whole reason we're talking about this, because we'd like to develop just a wee bit of understanding of statistical physics. And if you find this stuff interesting, especially if you go get a physics degree, you might find the subject of statistical physics or statistical mechanics very stimulating indeed. Okay, so by replacing the 6 with an n, we can now apply this formula to a similar problem, but any number of balls, maybe 1,000,000. So yeah, let's, I'm gonna get my calculator out. I won't write anything down on the screen. I'm just gonna do this out loud or verbally here. What if you had 50 balls zipping back and forth between these boxes randomly, many times per second, and then you go freeze time once a second for one of those freezings or snapshots? What are the odds of finding all the balls, all the particles in one box? Well, they could all be in the left box, they could all be in the right box. It's the same problem, but now the n is 50. So what is 1/2 to the 50th power? Let's see here. 1/2 in my calculator raised to the 50th power, and then I multiply that outcome by 2. The probability is basically 10 to the negative 15. That's 1,000th of 1 trillionth. Wow. So you can see that the probability of this outcome drops very rapidly as the number of balls increases. It makes sense, right? I mean, what are the odds that you would find all 50 balls in one box? Well, we just calculated it, or I just calculated it at something like a 1,000th of a trillion. It's much more likely to find 6 balls in one box. Okay, so now we can get to the actual problem. Here's what they told us, that of those 10,000 times that you checked on the configuration, you took a snapshot, 80 of those times, all of the balls were in one container. And from that information, we're supposed to figure out how many balls there are. That is part A of the problem. Okay. Well, think about it. If that desired outcome occurred 80 times, and you did this procedure 10,000 times, I say procedure, but it's just the act of freezing time to look at the number of, to look at the configuration of the ball. So of those 10,000 times that you take a snapshot, 80 of them saw all of the balls in the left box or all of the balls in the right box, which is the situation that we just looked at in the formula above. And of course, we can chop off one of those zeros. That would be 8 out of 1,000, 0.008. So 0.8% of the time, you find all of the balls in just one box. So that's the same as saying, you know, you can imagine if you've already found this result for 10,000 tosses or 10,000 snapshots, then if you go take another 10,000 snapshots once a second, then you can expect that roughly 0.8% of the time as well, you will find all of the balls in one box or the other. So in other words, the probability of finding all of the balls in one box is 0.8%. And that tells us already that we've got more balls than just six, because with six balls, you have a 1 in 64 chance of finding all of them in one box, and that's greater than 0.8%. So we know we've got more balls than six, but we have way less balls than 50, because if you had 50 balls, then the probability would be nil, bupkis, practically zero. So it's somewhere in between six balls and 50 balls, probably a lot closer to six balls. Okay, so all we have to do now is set our probability equal to 0.008 or 0.8%. Equate that with our formula here. Remember, this factor of 2 right here accounts for the fact that there are two ways of achieving this desirable outcome of all the balls being in one box. There's the left box and the right box. N is the number of balls, and the 1/2 just has to do with the fact that each individual ball has a 50% chance of being in the left box, for instance. Okay, so let's set 0.008 equal to 2 times 1/2 to the n power. Solve for n. And the rest of it, I feel like my handwriting is getting worse. Let me try that. I can do better than that. Aim higher. Whoops. The rest is just math. So let's now find the number of balls. Okay, well, I suppose we could divide both sides by 2. And that would give us 0.004 equals, and 1/2, isn't that 2 to the negative 1? So I can actually write this as 2 to the negative n, right? Because 2 to the negative 1 raised to the nth power. That's what this is right here. That's 1/2 to the nth power. Remember the rule, when you've already raised a number to an exponent, and then you raise that whole thing to another exponent, you multiply the exponents together. Some of you are rolling your eyes right now that I'm even telling you this, but I know that many of your classmates could use this review. Okay, so 2 to the negative what integer gives you 0.004? Well, you could just start guessing. In fact, it's probably easier to guess. Let me just write this off to the side. I'll switch the ink color here. I could have just left it as 1/2 to the n. And so 0.004 equals 1/2 to the n power. I mean, couldn't you just start raising 1/2 to various powers and seeing which power gets you closest to 0.004? Okay, so I'm going to do one right now. 0.5, we know it's more than 6 balls, right? We already established that. So 0.5 raised to the 7th power is 0.0078. Too big. So what about 0.5 raised to the 8th power? Oh, well, that happens to be really close to 0.004. So up here, I'm going to write that 1/2 to the 8th power is 0.0390625 exactly. This is awful close to 0.004. So I think we've already found our answer, because if you then go 1/2 to the 9th power, you're going to get a significantly smaller number. We would have to go with 8 balls. And remember, it didn't come out exact, because when you say that the probability is 80 out of 10,000, that just means that every time you check 10,000 times, you do the whole procedure, then you're going to find all of the balls in one box or the other roughly 80 times, 80 of those times. It might be 82, it might be 79, but it's not going to be 43. That would be totally improbable. Okay, so we're basically done with part A, but let's do this precisely. How would you go about doing this if it didn't occur to you to just start raising 1/2 to various powers? Well, here's what you do. I'm going to have to rewrite this equation. We need to use the change of base formula for logarithms. And off to the side, I'm going to derive that real quick. The log base A of some number x. Let's say we'd like to take the logarithm and we're using base a. A could be 10. It could be the natural logarithm base, which is e. Well, we can rewrite x as b to the log b of x. So I'm imagining some other base of a logarithm. If you take b and raise it to the log b of x, well, that's just x. This whole thing is really just x because the exponential function and the logarithmic function are inverses. Sorry, this is a b. And then I'm going to use that rule. I know this page is getting cluttered here. Can I? Yeah. So let me remind you down here in the corner of this rule. The log of x to the c, I'll say. You can bring that exponent down. That's c times the log of x. Well, this whole thing, let me get the highlighter. Yeah, this presentation of this problem is turning out to be quite a bit longer than I expected. But hey, we're being thorough. This is like my exponent now. It's like I'm taking the log of b to a power. So I can pull that power out front and write that as log b of x times the log a of b. So look at the far right side and the far left side and solve it for log b of x. I'm solving for this term. And here it is. Log b of x is the log a of x over the log a of b. Okay, I need to get rid of some writing in the corner here to free up space. Here's how you can think about this formula. Let's say this is an, oops. Let's say the letter or the number b is an inconvenient base because your calculator doesn't have a button for calculating logarithms in that base. Inconvenient base. But this other number a is a convenient base. That says convenient. Okay, so maybe you've got a log base 10 button on your calculator. That would be A, but you don't have a log base 2 button on your calculator because most of us don't. I don't have a log base 2 button on my $10 Casio. I don't need one because I know this formula. So you could say it this way. The log in the new base is the log in the old base divided by the log of the new base in the old base. Is that even helpful? Maybe it's just easier to memorize how to do it, like if you've done it a few times on your calculator. I think I need a new page here, but I'm going to select the equation that we need here, which is this one. I don't know if you can see the dotted line that's appearing on my screen here. Okay, copy, go to the next page, paste, brilliant. It worked. Okay, so let's take the log base 2 of both sides. No, not the log base 2, the log base 10, let's say. So log, where's my pen? Log 10 of 0.004 equals, you know, I'm starting to realize, did I even need that formula? No, I just spent all that time presenting that formula. I don't even think we need it. Oh, okay, so that's the log 10 of 2 to the negative n. Okay, well, I'm going to evaluate the left side in my calculadora, 0.004. I take the log base 10, and I get negative 2.398. I'll round to 3 decimal points or decimal places. And then I'll use that rule. I'm going to bring down the exponent, so that's negative n log 10 of 2. Yeah, we didn't need the formula. but aren't you grateful that you got that little review? The minus signs cancel. We take 2.398 and we divide it by the log of 2. That's the log base 10 of 2. Okay, so 2.398 divided by log of 2. I'm doing this on my calculator, and I get 7.96, I'll call it, which is awful close to 8. As expected, the number of balls is much closer to 6 than it is to 50, because the probability that we found, I mean, if it happens 80 times in 10,000, that's about a percentage of 0.8. That probability is much closer to the probability of finding all the balls in one box if you've got 6 balls than it is to finding all the balls in one box if you've got 50 balls. Okay, that's part A of the problem. But let me go back and make one more remark about why the way the problem was posed in your book is problematic. And in order to do that, I think I need to copy these 2 boxes. So hang on a second. All right. So here's why the way the problem is posed is problematic. They tell you that once a second, you randomly move one of the balls to the opposite box. But then they also say that once a second is how often you observe the total configuration. And that's why, if that were the case, the reasoning used that we just used in solving the problem would break down. Because supposing you're talking about a very large number of balls, like 100, if on one of your observations you happen to encounter the extraordinary scenario of all 100 balls being in one box, of course that's practically impossible, but supposing you had found that, then 1 second later, when you go to take a snapshot again and view that configuration, there is no chance that the balls are now evenly divided. I mean, all that can happen is that one of the balls has moved. So in other words, if at one particular snapshot, all 100 balls are in one box, then the next second, you know that there's going to be 99 in one box and 1 in the other. So all possible configurations are not equally likely. And the whole reasoning here depends on each configuration being equally likely. So if I go back to the very first page here, and this program is being slow. Okay. Remember, every time once a second, you observe the configuration of all the balls, that's equivalent to having done 3 coin tosses in a row. Toss the coin 3 times, look at the outcome. Toss the coin 3 times, look at the outcome. You're doing that every second to make a connection to the problem at hand. And the idea is that each of these 8 outcomes has to be equally likely every time you toss the coin 3 times. Maybe you got HHT, maybe you got THT. All of those are equally likely. But that doesn't work anymore if, this is a real subtlety in this problem. If you're actually switching the balls around once a second, which is the same frequency as the frequency at which you're looking at the configuration, that's not going to work at all, because once you've determined what the configuration is 1 second, you have a lot of information, and you've now excluded a great number of possible configurations the next time, right? If in the first second you see this configuration, then in the next second, the configuration of 50 balls in one and 50 in the other is actually impossible. So the more I think about it, the more I realize what a blunder this is. Somebody should have realized that when they wrote this problem. So the way to fix this problem is to think about like actual gas particles, which are multitudinous, and they're zipping back and forth very quickly. So let's just say there's like 1 billion rearrangings of these particles per second. And because there's so many rearrangings, so chaotic each time, then once a second, which is much less frequent, when you go to observe the whole configuration once each second, all possible configurations are equally likely. So the act of observing the configuration once a second is equivalent to tossing all 3 coins and looking at the overall outcome. Okay, so that's the main difficulty with the way this problem is posed. Now, part B, you can very intuitively answer They're asking, what's the most likely configuration? I'll go back to, well, let me just sketch it now. Since we know we're talking about 8 balls, we've already determined that. Obviously, the most likely outcome is 4 balls in each, because anything else is not symmetric. Like, why would there be 5 balls on the right side but not 5 balls in the left? It's got to be this. Now, how do we explain that? Well, what you could do is plot number of ways of having a desired outcome versus that outcome. So I'll say, how about number of balls in the left box? Okay, so we've got 1, 2, 3. These are the possible number of balls we could find in the left box, and I actually left out 0, didn't I? Have to include that one as well. How many ways are there of having 0 balls in the left box? Well, there's only one way, because all 8 balls would have to be in the right box. So I'm going to draw a bar of 0 height. Okay, how many ways are there of finding 1 ball in the left box? Actually, there's 8 different ways. If you numbered all of these balls, etc., there's 8 different ways you could find a single ball in the left box. You could have ball number 1 in the left box, or ball number 5, etc. So I would draw a bar that's got a height of 8. Wow, this is really sloppy. How many ways are there of finding 2 balls in the left box? Whoa, as soon as you start to think about it, you realize there's a lot of ways. You could have balls 1 and 2 in the left box, or balls 1 and 3, or balls 5 and 7. Okay, I'm not going to count them, but you can already see that bar is going to be, well, that was really bad. That ball is going to be way, or bar, I should say. This bar will be way higher than this one. How many ways are there of finding 3 balls in the left box? Tons. You could have balls 1, 2, 3, or balls 5, 6, 7. So that bar, this is not to scale. I'm not even accurately representing the difference between these two. And then, of course, how many ways are there of finding 4 balls in the left? It could be balls 5, 6, 7, 8, or balls 1, 2, 3, 4, or balls 1, 3, 5, 7, etc. That's going to be the tallest bar of our straight off the page, the tallest bar of all, I meant to say, straight out of the page. And then the other side is going to be symmetric with respect to the first side. How do we know? Well, think about the very last one here, or 7 balls. How many ways are there of finding 7 balls in the left box? That's the same thing as asking how many ways are there of finding only 1 ball in the right box? Well, the number of ways of finding 1 ball in the right box is the same as the number of ways of finding 1 ball in the left box. So that's why the height of this bar should be the same as the height of this bar right here. Okay, so it's going to be a symmetric distribution. Like I said, you could have drawn this better when you were still drinking apple juice out of a thermos, but I'm still getting used to this tablet. Okay, so that's how you would answer that question rigorously. But using my symmetry argument, or just common sense, right? We know that the most likely outcome is 4 balls on each side. Okay, so what's the takeaway here for this statistical mechanics stuff? Remember, Avogadro's number is order of magnitude in Avogadro's number 10 to the 23rd. So if you had 1 mole of gas particles that were zipping back and forth between these 2 containers, and you froze time and looked at the configuration, maybe now you have a sense of just how unlikely you would be to find all 10 to the 23rd balls in one box or the other. Because remember, even for 50 particles, we saw that the probability was like 1,000 of 1 trillion. Imagine how low that number is for 10 to the 23rd. And that's why in statistical mechanics, you see logarithms all over the place, because you're dealing with numbers so fantastically large or fantastically small
it's really inconvenient to use regular numbers. You can't be writing 10 to the negative trillion on a piece of paper all the time. That's annoying. 10 to the negative trillion. Okay, so that would be, a bunch of zeros. I think I got them all. Super annoying. So instead, you start dealing with logarithms. Okay, I'm really embarrassed by my modern art here, this Picasso I've drawn on the last page. Some surprisingly challenging concepts necessary to solve this problem. Bye-bye.